Hello science fans and welcome to SHE-ensya. Today I share a special video that is an updated version of the talk I gave at the 40th anniversary of the Philippine-American Academy for Science and Engineering. Here I talk about my passion about combining traditional ecological knowledge management systems and cutting-edge genomics technologies to help our farmers and fishers here in the Philippines. The new Sustainable Development Goals include a significant number of interconnected objectives related to agriculture and food. SDG 2, for example, focuses explicitly on food by seeking to end hunger, achieve food security, and improve nutrition and promote sustainable agriculture. But multiple other goals relate to challenges in the food system. SDG 1 focuses on poverty reduction, which is something that our fishers and farmers in the Philippines would need to benefit from considering they are among the poorest of the poor in the Philippine society. It is quite tragic that more than a third of the people who are growing and producing our food live beneath the poverty line. Sustainable agriculture also plays a significant role in achieving the objectives of SDG 6 on water, especially considering 80% of our freshwater consumption is due to agriculture. Then there's SDG 12 on sustainable consumption and production, which currently seems like an additional burden to our fishers and farmers who are worrying about increasing yield and their survival over changing their practices to accommodate for sustainability. Climate change is one of the reasons why our fishers and farmers are having difficulties in maintaining and increasing their yields. So any actions towards SDG 13 on climate change mitigation and adaptation could certainly help, especially since 14% of our total population and 42% of our fishing communities are threatened by storm surges. And as we design programs on SDG 15, on land use and ecosystems, I hope we don't forget about our indigenous communities who make up 10 to 20% of the Philippine population, who are currently grappling with the challenges of agriculture as they face land grabbing and violence. Sustainable management of fisheries also feature prominently on SDG 14, on marine resources and oceans. But our fishers are seduced by the higher returns of the marine ornamental fish trade, which have lowered the survival and productivity of our reefs. To learn more about the environmental impacts of the marine ornamental fish trade, please watch the video that will pop up over here at the end of this one. The Philippines is still primarily an agricultural country, despite the initial plans to make it an industrialized one by the year 2000. The country's agriculture sector is made up of 4 subsectors: farming, fisheries, livestock, and forestry, which together employ 39.8% of the labor force and contribute 20% of our GDP. One of the most pressing concerns of the agricultural sector is the rampant conversion of agricultural land into industrial parks, subdivisions, and resorts. In fact, as early as the 1990s, the nation was losing irrigated rice lands at a rate of 2,300 hectares per year, and it has been increasing over time. Small landholders find it more profitable to sell their land for cash, especially since they lack capital for seeds, fertilizers, pesticides, and wages for hiring workers to plant and harvest the crops. Combine that with unsustainable practices and the emergence of new diseases, it is not surprising that soil productivity and marine catch have been decreasing over time. But I believe that's where research and technology comes in, through the creation of practical innovations that can help our fishers and farmers maximize their limited capital. We can aid our agriculture industry. I was first exposed into agri-tech as a young student in the field of molecular biology and biotechnology. My thesis work then was focused on the development of biotechnology techniques for the abaca industry under the mentorship of my advisor, Dr. Vermando Aquino. The Philippines has always been a top exporter of abaca, but a combination of typhoon damage and blighting brought about by various viruses, our abaca yields have been reduced over time. Our team at the National Institute of Molecular Biology and Biotechnology during the early 2000s were trying to find a way to create a variety immune to the abaca bunchy top virus. The bunchy top virus is the most injurious among the three diseases that affect abaca in the Philippines. Fast-spreading, infection by the abaca bunchy top virus causes abaca plants to become severely stunted and bushy. Crops barely even reach a meter in height. Other symptoms include chlorotic streaks, and the young leaves barely reach adult sizes. The goal of our project back then, as funded by the Fiber Industry Development Authority, was to develop virus-resistant cultivars of abaca using modern biotechnology. My role then was to optimize genetic transformation techniques for abaca, specifically Musa textiles Ni. The primary challenge was that abaca was a monocot, and it was prone to a process called lignification whenever it was wounded. The main function of lignification is to strengthen the plant vascular body. This process involves the deposition of phenolic polymers, so-called lignins, on the extracellular polysaccharidic matrix and can be triggered by tissue damage. And though this process is beneficial to the plant, this actually inhibits the successful introduction of foreign DNA into the plant using old-school genetic engineering techniques, as this was before CRISPR technology. The primary method that I was optimizing was the gene gun or the biolistics method. The gene gun works by firing microparticles like gold or tungsten coated with plasmids containing the gene to be introduced. The velocity and pressure from the microparticles allow them to enter the plant cells, despite the presence of the cell wall. And even if lignification were to occur, ideally, the plasmid has entered the cell. What's tricky about the procedure is balancing the different parameters of the experiment. Too much pressure would kill the plant tissue, but too little would prevent the microparticles from penetrating the cell wall. Too much microparticles would be too expensive, while too little means very little chance of success as well. I am proud to say that our team was able to successfully design a plasmid to carry the gene that would make the abaca resistant to the abaca bunchy top virus. We were able to also successfully optimize the genetic transformation techniques. But despite our efforts, perhaps the Philippines was not yet ready for modern biotechnology back then. When I graduated from college back in 2007, genetic engineering received strong condemnation from various groups, ranging from the academe to activist groups. Farmers who were willing to try out the new technology suffered vilification, scorn, and even terrorism, to the point that their hard-earned crops were burned to the ground. It is quite ironic that as GM crops all over the world burned, food scarcity and poverty remained big problems. And it is perhaps fear and the lack of our proper science communication has limited the progress of this powerful technology. So I ran away, quite literally, to the mountains. I decided to pursue ecology and the management of natural resources for my master's. I wanted to study the natural systems that would help us maximize food production and learn firsthand about traditional practices in farming. But what literally took me to the mountains was my fascination with REDD+. REDD+ stands for Reducing Emissions from Deforestation and Forest Degradation, and the role of conservation, sustainable management of forests, and enhancement of forest carbon stocks in developing countries. It was first negotiated under the United Nations Framework Convention on Climate Change in 2005, with the goal of mitigating climate change by improving the management of forests in developing nations. In the last couple of decades, various studies estimate that land use change, including deforestation and forest degradation, accounts for 12 to 29% of global greenhouse gas emissions. For this reason, the inclusion of reducing emissions from land use change is considered essential to achieve the objectives of the UNFCCC. Growing up in the province of Bataan, I remember many nights driving along the highway and seeing our mountains on fire. This was because we had local farmers and indigenous communities practicing kaingin, a slash and burn technique that hurts our forests so that they can grow their own crops because they didn't have land in the lowlands. So I decided that I wanted to focus my studies on upland rehabilitation techniques and apply them in my own community. But to prepare for that, I had to learn about traditional ecological knowledge management systems. Traditional ecological knowledge, also called by other names including indigenous knowledge or native science, refers to the evolving knowledge acquired by indigenous and local peoples over hundreds or thousands of years through direct contact with the environment. Part of the study that I had to do was to detect soil characteristics, which included its chemistry, its incline, and water infiltration properties. Considering that I wanted some of the local community to help me also, this is when I started learning about adopting some of our advanced techniques in the lab and creating low-cost alternatives for the local community that I was working with. It was also then that I had first-hand experience on the importance of science communication. I think it was one of the most difficult things that I had to do, explaining to a council of elders from an indigenous community that is already defensive about their culture that their agricultural practices are unsustainable and that they should consider alternative methods. Leaving behind some wooden frames, tin cans with holes poked at the bottom, and pharmacy-bought thermometers with the local sangguniang kabataan in the barangay, I went into my first foray into citizen science without even being familiar with the term. Eventually, my path led me back to molecular biology, this time studying mangrove crabs under the NSF USAID Peer Project of my PhD advisor, Dr. Menchi Lagman. Our goal for the USAID project was to identify the connectivity of the Philippine populations of alimango. But as we went on field, we realized that our fishers had a bigger problem on species identification at the juvenile stage. And this affects our fishers greatly as fish ponds are typically stocked with purchased juveniles. And since the three dominant species in the Philippines have varying growth rates and market prices, cannibalization and lack of optimized conditions limit our productivity. This led us to the use of molecular methods to create a non-molecular approach to identifying juvenile alimango. With collaborators from De La Salle University's College of Computer Studies, Ms. Courtney Ngo and Ms. Cheska Laguna, this identification method eventually transformed into the free mobile application called Crabifyer. It makes use of convolutional neural networks to detect subtle differences in the carapace shape of early developmental stages of crabs. In the past year and a half, with funding from DOST PICAARD, our crab tech team has been busy deploying these technologies, collecting new information on traditional practices, and validating these practices in the laboratory. In the process, we have trained ourselves to teach in local languages and have made translations of our teaching materials in Filipino, Ilocano, Bisaya, and so much more. We have been very lucky that many fishing communities, their local government units, the local arms of the Bureau of Fisheries and Aquatic Resources, state universities and colleges, and even high schools have been very welcoming to us. So if you or anyone you know might be interested to learn about Crabifyer or the other techniques that we use in the lab, such as cheap or low-cost molecular biology and programming techniques, please don't hesitate to contact our team through my email at shona.abeledo@dlsu.edu.ph. We would certainly be very excited to help you. So before I end this talk, I would just like to remind everyone that a majority of the world's poor lives in rural areas, where farming and fishing, predominantly by smallholders, are the central economic activities. Large increases in agriculture and aquaculture investment will be needed both to raise incomes and increase the supply of food sustainably. But apart from that, we also need a synergy, a mosaic, of the old and the new, traditional practices with modern biotechnology, in order for us to create an agriculture industry that is sustainable while increasing our food production. And that's it for our SHE-ensya special for today. I hope you were able to learn something on the importance of both traditional and modern biotechnology in the field of agriculture. If you did, I hope you can give this video a thumbs up and also subscribe to our channel. If you have any comments, questions, or suggestions, please don't hesitate to message me, your resident Filipino scientist, in the comments section below. Thank you very much, and see you around!